Okay, so today we're going to be doing the aluminum foil lab. So we have a list of materials here, and we're going to be trying to determine how the relationship between density, volume, area, mass, and all that jazz. So I have a ruler, I have some aluminum foil. I do not have a micrometer, which would measures the thickness of a very thin piece of material, but it turns out we don't really need it, only just for verifying our answer. Some scissors, of course. I have an electric scale. I do happen to have a graduated cylinder, which I have right here. Some water, of course, and then I'm going to use a calculator. So let's go ahead and let's get started. Okay, so I have here the scale and the graduated cylinder, and then I have the three pieces of aluminum that I cut out very carefully. So here is the one that is 10 centimeters by 10 centimeters. Here's 20 and then 30. I didn't do the cutting on camera because it's really boring and kind of noisy, but those are the pieces. So if we look back at the procedure, the next thing to do is to calculate the area. So we'll put that in the data table, but I'll let you do that on your own. So 10 by 10 is just going to be 10 times 10, 20 times 20. And then we need to use the balance to measure the mass of the aluminum. So I'm going to actually first crunch up the aluminum so that it will fit on my scale. So here's my scale. I'm going to turn it on. It says hello, how nice of it. Here's the 10 piece. I'm just going to fold it up enough that I can put it on the scale. And it looks like it weighs 0.26 grams. So this one's 0.26 grams. This one I'm going to crunch up. And this one weighs 1.11 grams. So 1.11. And then this bigger one weighs 2.48. 2.48. Okay, so here are my data table. So these are the masses that I measured. The volume of the water is measured in this graduated cylinder. I used a pipette to get this to exactly 10.0 milliliters, which you won't be able to see very well. So I'll have to read that for you. So we're going to start with just the water and the aluminum just for the smallest one. So here I've crunched up these even further so that they'll fit into my graduated cylinder. So this looks like it's at exactly 10 milliliters. So I'm going to drop the small piece of foil in here. And unfortunately, it is floating. So I'm going to need to compress it more so it will sink. Okay, we're back. I managed to scrunch these guys up even tighter. So this should sink now. And it does. And it looks like it was displaced by about half a milliliter as far as I can measure. So I'm going to put that in my data table when I get around to it. So half a milliliter. Here we are. So we'll say it was 10.5. Now I don't actually need to change to take out this piece of foil because that'd be troublesome. Instead, I'm just going to assume that my new starting volume is 10.5, and I'm going to drop in the next piece of foil. So this was originally the 10 by 10, the 20 by 20 foil. So drop that in there. And it looks like it just barely went under the surface of the water. So we'll count it, and this looks like it is around 10.3, we'll say. So 13, that is, 10.3. Kind of, actually, upon reading closer, no, we'll call it 10 point, we'll call it 12. 12, or maybe even 11.9. I'm going to use that as the volume for the last one, 11.9, and then I'll drop the biggest one in here. And as you can see, I had a little bit of trouble getting them all in there, but eventually I was able to measure the volume. So yeah, after adjusting my measurement for the second one down to 11.6, then I found the volume for the 30 centimeter square was 14.0. So if I subtract these numbers, this one looks like I had a volume of 0.5 as we measured it. This one had a volume of 1.1 as we measured it. And then this one has 14 minus 11.6. That looks like 2.4. Okay, I guess we can go ahead and put these areas in here. I'm not fooling anybody. So 100, or 10 times 10 is 100, 20 times 20 is 400, and then 30 times 30 is, of course, 900. And of course, I forgot to show those values as I was doing it. So here are the volumes that we were talking about. These are the calculated volumes after we take the difference. So we took this value here, and then we subtracted it. Just put a big minus sign here. And that gave us this value, or the negative of this value. And then over here, these are the masses recorded, and these were the areas of the 3 different cubes. So for calculating the thickness, we're going to have to do a little bit of math. So this is what we're going to show next. Okay, so to measure the thickness, the thing you need to know, however, is that 1 milliliter is the same thing as 1 centimeter cubed, which means that in order to find the volume, if I know the volume in milliliters, what I really know is also the volume in centimeters cubed. These area is in centimeters squared. So if I take my volume and divide it by the area in centimeters squared, well, let's just do the first one for an example. So my volume equals 0.5 centimeters cubed. And that is getting divided by, can I underline this? Cannot. That's getting divided by, I'll do it manually, that's getting divided by 100 centimeters squared. Bum, 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 bum. And so let me just draw a little dividing line here. There we go. So if I do this division, the centimeters squared will cross out, and the centimeters cubed will eliminate 2 of the 3, so then it's just 1 centimeter. So then when I divide these 2 together, I get on the other side of this equation, or divide the volume by the area. Yeah, it should go down here and say divided by the area. This will give me the thickness. This is what I'm getting at. So the volume divided by the area should give me the thickness, which in this case will be 0.5 divided by 100. So volume divided by area, that's volume, that's the area divided. Thickness will be 0.5 divided by 100. So that's because I know a milliliter is 1 cubic centimeter. So thickness, or volume divided by, it's going to be a small number, of course, divided by 100. And that gives me 0.005 centimeters. So in this case, this equals 0.005 centimeters. So that's how you're going to do this calculation. So for each of these, you're going to take the volume that you found divided by the area that you have to get your estimate for the thickness, 0.005 centimeters. Obviously, that's very thin. I mean, that's less than 1 millimeter. So these numbers should, in theory, because I use the same foil, all be the same. Now, they won't all be the same. And the reason for that is because measurement error. And I wanted to talk a little bit about that. So a lot of these questions have asked us about the precision of our measurements. So I answered these questions for you based on the measurements that I took. You should be answering these questions here yourself. I obviously don't have a micrometer, so you can't answer this question. However, you should be able to calculate the density of the foil if you remember that density is equal to the mass divided by the volume. So you have the mass and you have the volume, so you should be able to calculate the density. Again, this should be the same for all of them, but I would suggest checking for each of them and then maybe taking an average. You would expect the thickness to be the same for the whole roll because it's the same roll of aluminum, but I've looked at the calculations already and you won't find that they're exactly the same, and that's because of some possible errors in our measurements. And I would say one of the biggest factors that measures the precision here is air bubbles. So when you crunch up a piece of aluminum foil, there's actually air trapped in there, and we noticed that when some of our pieces of aluminum foil tried to float. So if you have if you have extra air trapped in there, that ruins your calculation of the volume because that extra air isn't being counted against the mass of the aluminum. Sorry, the volume of the aluminum. So that's one thing. You can probably think of at least one more. Okay, so I think that summarizes what we got in the lab. Here again is the data table, which I'll leave up on the screen. You should be able to calculate the last two thicknesses now that I've done the demonstration. And then I will share this document along with the video in the description so that you too can finish up the lab and answer the questions. Okay, thanks. Have fun.